that pair of clauses has a set of support. At least one of those clauses has set of support. That means it has gold blood in it. It's either a gold clause itself or a clause that was derived from a gold clause. Intuitively, this makes sense, right? Because the most reasonable case for proving theorems is starting from a knowledge base that's not inconsistent all by itself. So the only reason inconsistency must be coming is because of the not alpha. And so eventually you should be resolving some goal clause or some set of support clause with somebody else to get the negative clause, get the empty clause. Do you see what I'm saying? So this heuristic, if I use this, that will cut down a whole bunch of resolutions, right? Because I'm saying I'm never going to touch two clauses if at least one of them doesn't have set of support. That cuts down the number of children you actually generate. Okay? And it actually also turns out to be a complete heuristic. In the sense that if alpha can be proved with the full search, it can also be proved with this heuristic. Now the question still remains as to whether the proof you came up with is the shortest proof or not. But we don't care about it. We never talked about the length of the proof here. We just said prove it and we're done with it. So the A-star search analogy doesn't work here because A-star search actually considers the number of resolutions you need in some sense. But here you don't care about the number of resolutions. If you can prove the empty clause, if you can get an empty clause, you're done. And then you're happy. Okay? And set of support is actually complete. There is another idea called linear input form, where you say at least one of the clauses must be a blue clause, must be an input clause. Not just royal blood or blue blood, just the blue clause. One of the clauses should always be an input clause, and the other can be anybody else. It turns out that cuts down the number of resolutions you can do even more, because the initial clauses are much fewer. And the database keeps increasing, but the initial clauses were initial clauses, and they don't keep increasing. So one side of the page has been fixed to a much smaller set. This is called linear input form strategy. It's a great heuristic. It's incomplete. There may be proofs, there may be theorems that are actually provable, that there is actually an empty clause, but if you just use linear input form strategy, you won't find it. So completeness, incompleteness is sort of like admissibility here. Now you would think anybody would use incomplete heuristics? You think anybody would use inadmissible heuristics? If you remember that far back, you know that the world at large uses inadmissible heuristics. Computer science is knowing what is the right thing to do and choosing not to do it. Okay? So basically, admissible heuristics sometimes might be inefficient, you use inadmissible heuristics. Similarly, people do use incomplete strategies. I rest my case by saying Prolog uses linear input form. And Prolog is the big daddy of them all. That's the closest you ever came to AD logic in your life. And it uses linear input form. But it also depends only on essentially modest ponens, complete non-cross databases. And there it turns out to be actually complete. Okay, so this picture I'll just show you what you might be thinking. This is essentially showing all the resolutions that would be done on a certain database by just breadth first. The way you do breadth first is first you take the very first level, you take two classes from the first level. And the second level, you take a class from the second level and any class from either second or first level. And the third level, you take a class from the third level and any class from the second, third, or first level. That's how you ensure that the loop is systematic. It will never, keep on repeating the same resolutions again and again. So that is the number of resolutions you do for some simple scenario for breadth first. And if you do set of support, you see there are fewer lines. fewer resolutions being done. If you do linear input form, you see even fewer lines. Again, fewer input resolutions being done. This turns out to be complete. This is not. This is certainly complete. Because you're doing every particular resolution. Yes, sir.
Could you say that you can use things from the same level? Because the pictures don't show that.
No, so breadth first, basically breadth first is doing is in this particular case, so notice here, this one is taking one from the most immediately previous level and the other from either the previous level or the level before it.
Oh, so it's previous?
Yeah,
Okay.
just previous because, and then this will be the next layer and then you will again come down. But the bigger thing I want you to understand is no magic in anything in life. If there is magic, you can't do computer science. Theorem proving is just search. It's boring search. That's what is good about it. So you can write a program and go home. Okay? The second thing I want to say is the mad chase for empty class, or how people see empty classes everywhere, especially under time pressure during exam. And I'll show you some examples where people find empty classes when there aren't any. Okay, so these are these are basically don't do it. So these are the usual errors people do. Okay, again, look, there are two different things that we do. One is, my whole point of doing that previous discussion is, nobody in their right mind should be doing theorem proving by hands. They should write a computer program. But on the other hand, we have exams sometimes where people actually try to do something by hand. At which point they'll start of hallucinating empty classes. Okay, and the way you hallucinate empty classes can also go into your program and it can make mistakes too. So if you don't do this wrong here, you also won't do it wrong in the program. Okay, so one is, you must have everything in CNF classes before you can resolve. Okay, so if I have something like P or Q, I'm sorry, if you have something like P and Q, and not P and Q, resolution is not allowed there. Do you see what I'm saying? They are not causes. A lot of people will say, there's something and it's negation, so there's an empty class, I'll put it there and go home. Actually, it's not inconsistent at all. Okay? The other thing is, similar to this one, you cannot resolve everything away at the same time. P or Q and not P or not Q. Very tempting. Right? I can just say P and go away, Q and Q go away, so the whole thing is empty class. No. You have to pick one literal and its negation and remove there. That's it. In fact, if you pick any one literal, let's say P or not P, and remove them correctly, you get Q or not Q. Is Q or not Q empty class? It is anything but empty class. Q or not Q is true. And yet it looked like a syntactically very plausible thing that you might do under stress. Again, this is stuff that logic textbooks don't have to tell you, because people are not supposed to be intelligent, right? But I know that some of us are, so it's useful to know the kind of errors that you can. Okay, so that's two things that you want to avoid doing. And otherwise, it's essentially, if you are trying to find like a proof, basically, you have to realize that there is no magic here. You're supposed to write a search algorithm that goes through all the possible things. If you're trying to do it by hand yourself, it's like trying to find a path in a very big maze using A-star search yourself. If it's a small maze, you might see the path. If it's a big maze, you will also do all sorts of errors. That's why you have the search algorithms. Yes.
On that side right there, the red lines between not SG and SG, is that a conjunction? Is that not SG and SG?
This one?
Yeah.
No, I'm resolving. Not SG is being resolved with SG.
Okay. I'm just confused because the one that you just showed was, I think, Q and not Q, correct?
Yes, I mean, so this one is fine because this class is not SG and this class is just SG. And I remove one literal and its negation and keep whatever else is there. What is left is here.
Okay. So on the other one, we're Q or not?
No, in the other case, you are having P or not, P or Q and C, not P or not Q. Yeah. You have P or Q or not P or not Q. And you try to get rid of both of them at the same time. You try to find shortcuts which don't exist. Okay? Of course, another thing is people forget to negate the goal before adding it to the database. That's something very important because you can only get empty class after adding the goal, after adding the negation of the goal to the knowledge base. And then see if you get anything else.
Do you replace it?
Which one?
Like when you add it, are you actually like replacing with the one that wasn't negated?
Yeah, the only time goal actually gets in is as the negated. That's yes.
So after we resolve them, we would add Q or not Q to the database, right?
In this case, you will have to add Q or not Q to the database. Not a empty class.
Can we prove anything with Q or not Q for that to be an empty clause?
No, again, so this is the other thing. Everything you are adding to the database is valid given what you started with. But remember, if you are doing resolution refutation, you don't know whether you did some resolution that involved a goal class, that is negated goal class. So it's not clear that this thing came directly from the input classes. So really you can't say anything about this until this sort of leads eventually to an empty class. If on the other hand you're doing only forward resolution, if you're only doing forward resolution, okay, then you don't actually keep anything about goal in the database. Okay, you just basically start with the input class and keep doing, so basically you do this particular thing except you never even add DG. And you keep doing resolutions until you find the goal class as the result of one of the resolutions. So instead of looking for is there an empty class, you look to see is there a goal class that I just put. That's forward. Unfortunately, forward is not complete in the sense that forward resolution requires additional simplification such as Q or Q is Q. That's why everybody just does resolution refutation. And it becomes a bigger issue for first order logic. The resolution refutation is only thing that actually guaranteed. Yes?
If we had a KP that was all in form form, we do the same algorithm instead of resolution doing all these components.
So, first of all, you have to realize that this is the other cute thing. Since resolution is a complete rule, everything else is a subset of resolution. Right? So, the strange thing is if I can do resolution, let's see here. So, P implies Q and P, you get to say Q, right? That's what correspondence is. But resolution will do that for you too. Because this P implies Q is not P or Q. Resolve with P. Everything that you ever learned in your life is a special case of resolution. Very nice. Okay? Any other questions? Okay, so we already talked about the complexity of the propositional logic. In particular, it is coherently complete unless all the clauses are Hahn clauses, in which case it becomes a kind of a propositional prologue, and there it will be polynomial. That is, complexity is polynomial. One other special case where complexity is polynomial is everything that you can prove just by what's called unit resolution. A unit resolution essentially is yet another of these heuristics, where a third heuristic here is unit resolution. is one class should be a unit class. So one of the classes should be a unit class. Unit class means it's length 1. The good thing about unit classes is generally when you resolve, so remember, if you have a class of length k, empty class has length what? 0. Syntactically you are making progress if the derived classes are smaller and smaller length. Right? Otherwise you are not getting close to 0 class. Normal resolutions in general, let's say you take PRQ and not PRJ, it will give you PRJ. Length hasn't reduced. Worse yet, if I said P, R, Q, or M, and not M, R, A, or B, then I get a class P, R, Q, R, A, or B. The class length increased. That looks like negative progress. I want empty, and my classes are increasing in size. So one heuristic is to only do resolutions that definitely reduce the length, right? Because that's where the 0 is, you know. So if you ensure that one of the classes in the result of the pair of resultants is a unit class, then you are guaranteed that the new class would be smaller than the other class. So if I resolve PRQ with not Q, then I'll get P, which is a unit length. You see this? Now, if I only use this resolution, this idea, it's even better than any of those other ideas because there are so few unit-sized classes. And you just run, unit class with any other class, and then just do as much as you can go. And you'll be done very fast. And you'll fall out of the loop. But the problem is you can't say that theorem is not true. Everything you did with the unit resolution is still actually a relevant resolution. But the fact that you didn't get empty class does, if you did get an empty class, you're fine. If you did not, then it's not guaranteed that the theorem is not true. It's the same thing with this, right? If you did get an empty class with linear input form, it's guaranteed that the theorem holds. If you fell out of the loop without getting it, that doesn't necessarily mean that the theorem is not true. It only means that you need to find the way. Unit resolution is a huge thing. People run unit resolutions on databases to large bases to make them smaller, especially when you look at satisfiability problems. And it turns out that too can be run in polynomial. So you almost do this as a pre-processing step. In fact, one of the things people do is they just run unit resolution on the original database before you even add the negative goal to it, for example. Okay? So that's as far as the complexity is concerned. Okay? So at this point, I completed what I thought I completed at 20, which is basically propositional logic. But that's my life. Okay? So now the question is, now that you're done with propositional logic, what can we be doing with this? You understand propositional logic and theorem proving with it, at least in my mind, not necessarily yours. Okay. So the question is, what can you do starting from here before we go off to probabilistic logic? The world is wide open, it turns out. Okay. You can do all sorts of interesting things. From propositional logic, you can do propositional model finding, which is the Boolean satisfiability problem. Last class I mentioned Boolean satisfiability is the NP complete, and the conjugate of it is theorem proving, so it's co-NP complete. It turns out that satisfiability problems are just as useful as theorem proving. In fact, you know who uses satisfiability problems a whole lot? Intel, Motorola, every CAD company. Because the way you verify circuits, it turns out, involves essentially showing that there are no models where the bad things can happen. So satisfiability is actually used a lot in the industry. Okay? And I would love to do that. In fact, it is covered in chapter 7.6, that's section 7.6 in this same particular thing. But there's so many things we can do, but that's one of the interesting things. And it turns out that actually, if you think of satisfiability, and remember I kept saying knowledge is a constraint. Right? That's the whole thing I kept saying. Knowledge is a constraint. So if I get more and more SAT statements, propositional statements, I have more and more constraints. Model finding is finding a word that satisfies all these constraints. You see what I just said? So it actually turns out that Boolean satisfiability is actually a special case of another problem called constraint satisfaction problem. That is covered in chapter 6 in the textbook. The only difference is in Boolean satisfiability you assume you have discrete valued variables with true false as the values. In CSP you think you have multi-valued variables. Like for example, color can be blue or green or red or yellow. And then you might want to convert, let's say, a colorability problem on a map into a constraint satisfaction problem. And it turns out that anything that can be done as a constraint satisfaction problem can also be done as a satisfiability problem. And in fact, many people actually solve many of these problems as SAT problems. So you know enough about propositional logic that you actually understand. You're right at the threshold of satisfiability. I could have done that. I could have also done, now that I can talk about states as not just a set of real valued features, which is what we did for reinforcement learning. I can think of states as Boolean features. And then do state search, where actions will work on the states and change the state variable values. It would be a version of A-star search, and that's been called basically propositional or relational planning. So doing search where the states are represented as propositions is basically planning. That's covered in chapter 11. I could do that as a subroutine starting from here because you know enough about propositional learning. Third thing I can do is, now that I have logical statements, you can think of each of the logical statement as sort of a function. It's a Boolean function. If I show you a whole bunch of examples, I might be able to figure out, if I show you a whole bunch of words where the statement is true, can you write the statement? Remember, if I have P1 to P10 as the variables, and if I know that the formula I have in mind is P1, then 512 words will actually be consistent. Think of the opposite problem. I show you 512 words, and I say, can you guess what I'm thinking? You see what I just said? And you say, yeah, you're thinking P1. You learned. I show you 340 words. And I say, can you say what I'm thinking? And you say, yeah, I think you're thinking P1 and P2 implies P3 or P4. That's basically learning of the function I have in head that exactly covers the words that I gave you. That's logical learning. A particular form of logical learning that's very, 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 very popular is decision trees. I could do that and you'll pay me money. Because once again, this is the kind of thing that will come up in jobs, right? And machine learning techniques. Remember I showed you all these machine learning techniques that are being used in the industry, and logistic regression is up, and neural networks is somewhere in the middle. Decision tree is very quite high up there. It's a cute idea. Can be done. I mean, not with my speed, but it can be done very easily, and you can understand it very easily with what we have understood about propositional. Third, right? A fourth one is I actually can do first order logic, which basically tells you what exactly can you do. So you went from atomic states to propositional states, right? I can tell you what it means to go from there to relational or predicate representations. and what it means to go from there to functional, predicates with functions, which is first order. And in some sense, if you understand that, that's like first order logic, and basically it's very much parallel to some extent to propositional logic, but it actually tells you how the compaction of the knowledge can occur. At the atomic level, you have too many states. The propositional level, it becomes much fewer sentences. An interesting question is, if you have to write the rules of chess at the atomic level, it's basically going to be having 10 power 150 symbols, because there are 10 power 150 different chess states or something. And each state is a different number, S59, S90, 19,355 million or something. So if you were to write all what you know about chess in that proposition and that atomic form, it will be humongously large. If you write it in propositional form, it will still be humongously large, but it's a small humongous. The way you actually think of chess, it turns out, is you think in terms of first order logic. And that's just a couple of lines. That, if I tell you that, then you will be even more impressed at this whole idea of compactifying knowledge. Now, most likely, you're not going to get a Google job right away for that, because they'll ask you what's the decision trees, and Intel would ask you what is satisfiability. So I was wondering, which of these 4 things should I be doing here? Since I'm wasting your time, I should find what should I be doing here. I kept asking my students, Sriram knows that I was asking students in the lab, which one should I do for these guys? And then I also have, my son is into logic, and I asked him, and he said, why do any of these exclusively cover capsule networks? And you would be very happy. But no, unfortunately, no capsule networks. So rather than follow what my son said, I'm going to cover first order logic. In the next 5 minutes, I'll give you just the beginning, but next class I'll spend on first order logic. It's an idea that expands your mind. And once you realize that it is possible, then you will actually start realizing that much of what's going on in neural networks is in some sense atomic representations, or at most propositional representations. There are no relational representations. Actually, there are propositional representations at the real valued variables. There is no relationality. Capsule networks can actually be thought of in terms of bringing in structure that you can bring through relations and objects. That comes first time in first order logic and relational logic. So understanding it once is extremely useful. So that's what I'm going to do. So in the next 5 minutes, I'll only just show you the slides, but next class we'll go through them slowly. Okay. So if you remember, you saw this picture, and so we did propositional logic. I'm going to do first order logic, and then later on, after that is done, we will get to probabilistic propositional logic and spend almost 4 classes on it. Okay, and then it turns out there should be something called first order probabilistic logic. I have nothing to teach about it because it's still very much in the research level. A lot of people think it's like big deal. In fact, Stuart Russell, the guy who wrote your textbook, is a huge believer that the best way to do Brown's implementation is first order probabilistic logic, and he has this language called blog. Not blogs. He doesn't actually write blogs, but blog for him is first order probabilistic logic. But it's kind of still in research form, so we won't talk about that. And this I actually want to mention. In fact, this is the only slide I'll do. The rest everything else has a next class. Understand this, you'll be in very good shape as to what I'm trying to do for you. So, you talk about atomic representations already. We talked also about propositional representations. We will then talk about relational representations, things like loves, Tom, John. That will be relational representation. So the relation loves holds between object Tom and object John. I'm not objectifying people. That's what the logic does things. Okay? So object Tom and object John. Now it turns out that thinking of things this way is actually very useful. In fact, you can say this is nothing but loves dash Tom dash John. And if you say that, that becomes a propositional symbol. And it can be true or false. That also tells you, for example, that any relational language can be converted anytime you want into propositional language. But the fact that the relational structure holds makes things much more interesting. You can write things in way more compact forms. Okay? So that is relational representation. States are made up of objects and relations between them. And one of the things you get to do in the relational logic, for example, I can say something like, for all xy, loves xy implies not kills xy. You know, I'm an optimist. Okay? So you could write this. And it turns out this is a compact way of writing a conjunction of huge number of sentences. So for example, in your knowledge base, let's say you have Tom, John, and pen. Those are the three objects. Then essentially what I just said becomes, if I propositionalize it, it essentially says loves John, pen implies not kills John, pen. And loves John, John implies not kills John, John. And loves John, Tom implies not kills John, Tom. One little sentence, actually it's a huge conjunction of implications. I could just write it in one little sentence. This is how you make a huge body of propositional knowledge about chess into just a few sets of logical statements. This is quantification becomes very useful. And then to get to first order, essentially full first order logic, all you add on top of it is, in addition to relations are called predicates and objects, you also throw in things called functions. A function is an object producer. It takes a bunch of objects and produces a new object. I can throw in a function like father of, right? In addition to Tom, John, and pen, I throw in one more function, just one function symbol called father of. Now, how many objects, nameable objects are there in my world? There's Tom, there's John, there's pen, there's father of John, there's father of Tom, there's father of pen, there's father of John, father of. See where I'm going with this? One function, your happy world collapses into infinite number of objects. Now remember, the moment you have infinite number of objects, the way you propositionalize something is predicate name, an object, and an object.